Hi, in this video I'm going to give a brief and informal introduction to big O notation and its use in analysing algorithms. As developers, when we wish to analyse an algorithm, we are usually concerned with the best case, the average case, or the worst case runtime. For big O, we are focused on the worst case. We really are interested in how the runtime increases as the input n increases. Big O notation gives us a high level or a big picture overview of an algorithm's complexity. We could determine the total runtime by the cost of executing each instruction and the frequency each instruction is executed. However, thinking about that, the instructions will depend on the programming language, the compiler used, or the underlying machine architecture. By eliminating constant factors or lower order terms, we eliminate a lot of unnecessary detail, but we still maintain a reasonably accurate view as to which algorithm is better for our needs. There are some common examples that you'll see when studying big O. The first example that we'll see is constant time, or a big O of 1, and this represents an algorithm where the size of the input n has no effect on the runtime. For example, consider accessing an element from an array, pushing an item onto a stack, or some simple instructions that don't depend on the input. Further examples would include popping from the stack or adding to a queue. Next up, we have a big O of log n, or logarithmic complexity. The classic example here is binary search. Let's say we have a sorted array of 9 elements and we're looking for the value 4. We could start at the midpoint, in this case 5. We know that 4 is less than 5, so we can eliminate the entire right-hand side of the array. We can repeat this process, thus halving our search space at each step. Overall, this gives us logarithmic complexity. Next up, we have linear complexity, or a big O of n. Here, the runtime is directly proportional to the input size n. Using search as an example, but now with an unsorted array, in the worst case, we would have to iterate over the entire array. Here, n is 5, thus we've iterated over 5 elements. If we double the input here, now 10, we do double the work. A further example would be accessing an element from a singly linked list. We don't have random access, thus in the worst case we would have to iterate over the entire linked list. If the linked list has 10 items, we would have to iterate over all 10 items. Next, we have linear rhythmic complexity, or a big O of n log n, and a common example is merge sort. Similar to binary search, we divide the input in half at each step. However, we can't discard that half anymore. We still have further work to do. In this case, we have to merge the arrays together at the end. A simple way to think of it is we do log n work n times. Next, we have a big O of n squared, or quadratic complexity, where the growth is directly proportional to the square of the input size. The giveaway in code is you'll see nested for loops, each iterating n times. For example, looking at the pseudocode, we can see that the outer loop iterates n times, whereas the inner loop iterates n-1 times, thus overall giving us a complexity of big O n squared. Examples would be selection sort or insertion sort. And finally, we have a big O of n factorial. For example, if we're generating the permutations. Let's say we have 3 characters. Well, there are a total of 6 possible permutations. If we had 4 characters, there'd be 24 possible permutations, and if there were 5 characters, there'd be a total of 120 permutations. Other examples include travelling salesman and the brute force knapsack problems. We will visit these in a later video. The following graph highlights the rate of growth for the types of algorithms that I have just described. On the left-hand side, we could see order n factorial and order n squared functions. These have an incredible rate of growth, thus they aren't feasible for even small values of n. In the middle, we have a big O of n log n and big O n functions. These have a slower rate of growth, but still for massive values of n, these may be unfeasible. And finally, we have order log n functions and constant time functions. Obviously, constant time doesn't have a rate of growth, but O log n has a very slow rate of growth. These are feasible even as n becomes incredibly large. How does this look in reality? Well, in reality, we are actually often concerned with the constant factors and lower order terms. For example, if we're implementing algorithms for a standard library, these standard libraries are going to be used by a wide range of developers with a wide range of different use cases. Therefore, it probably is worth the effort to reduce constant factors and try to eliminate lower order terms. Or if there are small values of n for our input sizes. Therefore, the constant factors and lower order terms may still be very significant. Finally, thanks for watching. I hope you found this video informative. Please hit the like and subscribe button, and I hope to see you in a later video.